big is infinity? Well, there's not just one answer to this question. There's multiple levels of infinity, and some are bigger than others. The smallest level of infinity is the one we know and love. It is known as Aleph Null. This is the countable infinity, which is the set of all natural numbers. Say you have an Aleph Null amount of clones. If we took the first clone and moved it to the end over here, and insisted we order the clones from left to right, what number does this clone get? This last number of infinity is known as omega. While omega doesn't contribute to the total, it is an ordinal number, which means that it refers to its position, just like first or third. To go beyond, we simply say omega plus 1, and we can go all the way to omega plus omega. Since Aleph Null is the smallest infinity, there are higher levels of infinity that we can reach, and we can prove that with Cantor's diagonal argument. We're going to list out all the whole numbers to infinity. Now we can pair each of these whole numbers with real numbers between 0 and 1. Since they're paired up, they have the same cardinality, meaning they're equal. But infinity isn't large enough to list all decimals. We can still make new real numbers by taking the first digit of the first number, the second digit of the second number, and so on. Now we can change each of these selected digits by subtracting 1. Using this method, we can make a whole new set of numbers. It can't be the first number listed since the first digit is different, it can't be the second number since the second digit is different, and so on to infinity. This shows that there are more numbers between 0 and 1 than there are whole numbers. This new set of decimals creates our next smallest infinity, Aleph 1. Unlike Aleph Null, it is an uncountable infinity. By continuing to apply this method to each new list we create, we can go all the way to Aleph Omega, an absurdly high level of infinity. But infinity is no stranger to seeming absurd. Think of a shape that has an infinite perimeter but a finite area. It seems impossible, doesn't it? Well, in one of the first fractal curves, the Koch snowflake achieves this feat. We can prove this using Sierpinski's triangle. In just the area of this one fractal triangle, it has an infinite amount of triangles within it. Just take these triangles and rearrange them a bit, and there you have it, our paradoxical shape. The Koch snowflake can also be proved to have an infinite perimeter but a finite area using Zeno's dichotomy paradox. To picture this paradox, imagine you're walking towards a tree that's a meter away. To reach it, you first have to walk half the distance, then a quarter of the distance, then an eighth, and so on to infinity. So it seems that our meter-long path is now infinitely long, just how our Koch snowflakes seem to have an infinite area. This perception is very misleading. Think of it like this. Instead of a path, you have a square. You can halve the square to infinity, and it will always still have the same area, proving that our path is finite as well. And so we ask ourselves the age-old question, can we count to infinity? No, but our minds can take us beyond.
Yay.